Greetings. Welcome to our 27th episode of the FGI podcast series. My name is Tim Stark, and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign.
And hello, everyone. My name is Jen Miller, and I'm the coordinator of the Fabricated Geomembrane Institute, or the FGI.
On today's episode, we are going to focus on our March 23rd, 2021 webinar titled Design and Performance of Hazardous Waste and Low-Level Radioactive Waste Landfills, a 20-year case study. I'd like to quickly reintroduce our speaker, Dr. Rudolph Bonaparte, who is board chairman at Geosyntec Consultants, Inc., headquartered in Atlanta, Georgia. He previously served as president and CEO of Geosyntec for 20 years, building the firm from a startup to 1,200 employees in more than 60 offices in 6 countries. He is also a professor of the practice in the School of Civil and Environmental Engineering at the Georgia Institute of Technology in Atlanta. Rudy, thanks so much for joining us again.
Thank you, Tim.
Rudy, we had a large number of questions related to your excellent webinar on hazardous waste landfills. So we're going to run through them. For the listeners, we'll probably go through about 30 to 35 questions. So we appreciate your interest in the topic, and hopefully you'll be able to find your question and Rudy's answer here. Rudy, first question. What is the level of details needed to specify in geosynthetics design? Any recommendations on engaging geosynthetic suppliers / vendors early in the project?
Yes, I think in general, these designs require a high level of detail and specificity. And the more and the better the detail you give, the better the constructed product you get. So for example, on Fernald, our geomembrane specification ran to 17 pages, including tables with lists of properties and quality control testing that needed to be done and other things. And the drawings had, were highly detailed in terms of all of the geosynthetic components and connections and anchor trenches and those kinds of things. With respect to consulting with suppliers and vendors, I also think that's always a good idea when you're starting a project to learn about new products, new developments, whether new specs are available, whether the specs that a vendor is proposing has evolved over time with some new thinking into it. And so it's important to keep up to date with respect to those things.
Great, Rudy. Next question. Any recommendations on cell sizing for a hazardous waste landfill?
Yes, it's going to depend somewhat on the rate at which you receive waste. So you want, in my opinion, you would like your cells big enough to accept a year or two of disposal capacity, but at the same time not be so large you're capturing a lot of precipitation that becomes contact water so that you need to treat it. So you're balancing those things, and it'll be different for different sites. In our case at Fernald, we were looking at cell sizes of 6 to 7 acres, 350 to 400,000 cubic yards that would accept waste for a year or two, but weren't so large that they generated more leachate than we were hoping for.
Perfect. Was there a design requirement for the leachate head on the geomembrane not to exceed a certain value? Was the head calculated on the geomembrane elevation or on a different layer?
Yeah, so the value, I think, as most people would guess, is 12 inches. And that comes out of both federal 40 CFR 264 and Ohio Administrative Code ARARs. Remember, I talked about ARARs during the presentation. So it's 12 inches measured from the geomembrane at the low point in the cell.
Great. Next question relates to the ESR test, and they want to know what test method was used.
Yeah, we used for the geomembrane ASTM 5397 standard test method for evaluation of stress crack resistance of polyolefin geomembranes using the Knott's constant tensile load test. and we had a failure criterion of at least 500 hours, which at the time I think was the most stringent criteria that had ever been used on a project like this.
Great. What kind of long-term monitoring of the environment was undertaken?
As you saw in the presentation, we monitor the landfill itself, the leachate collection system and leakage detection system. And then we monitor the vadozone beneath the landfill using a vadozone monitoring system. And we monitor groundwater around the perimeter of the facility with a series of groundwater monitoring wells that are installed into the uppermost aquifer. There's also monitoring the final cover system that goes on and looking for a variety of physical parameters such as erosion, gullying, woody vegetation, which would be removed if it's observed, and things of that nature.
Great. Normally, landfill design tries to avoid penetrations through the geomembrane. Why are leak collection and leak detection penetrations through the primary and secondary geomembranes acceptable for this facility?
This is a little bit of a pick your poison question. Would you rather try to maintain a pumping system and a more complicated clean out system with a side slope riser with pumps for, let's say, 500 years? Or would you prefer a gravity system that basically is a straight shot pipe? And we chose the latter. So, but as we all know, creating penetrations can be challenging. And the traditional method, using boots with clamps and things of that nature, may not have the design life that we need. So we actually developed a special detail for the penetration that is a flat stock structure that you build right into the side slope of the facility. So all geomembrane attaching to the structure is onto flat stock. You're not trying to weld a geomembrane onto a round pipe. The round pipe is welded through a penetration in the flat stock. In fact, there's two penetrations with about an inch a gap between the two, so we could air pressure test the penetration as part of the CQA program, and then fill the gap that we use for air pressure testing with bentonite after that. So we feel like we have a very, very secure penetration. And in fact, there was a paper written just about the penetration by Jay Beach, who some of you may know.
Oh, yeah.
Entitled Innovative Geomembrane Liner Penetration for Long-Term Waste Performance at the Waste Tech Conference a number of years back.
Yeah, sounds good. Actually, if Rudy, I'll send you a message for that paper. We'll put it on the website with your webinar.
Great. I'll be happy to send it.
Great. Okay, next question. Was any clean soil needed to place the D&D waste, or was it all contaminated soil from the cleanup?
Yeah, it was all contaminated soil. We had an excess of contaminated soil. In fact, 80% of the material that went into the OSDF was contaminated soil.
Rudy, did you perform an electric leak location survey on each composite liner?
We did. We performed leak location surveys on the primary and secondary composite liners. And in fact, this was one of the first leak location surveys conducted with a geomembrane and GCL. So we were prototyping it to see how well it worked. We also performed a leak location survey above the primary composite liner in the gravel leachate collection layer after the gravel was placed, to make sure that the placement of gravel didn't induce any new damage, and we performed the leak location survey on the final cover system.
Great. Rudy, you touched on this a little bit. How did you manage contact stormwater / wastewater besides the size of the cell and controlling how long it was open?
We basically had the position that anything that falls into the cell is leachate. We didn't try to use rain flaps or things of that nature at that time. What we did do is we created in each cell a leachate catchment area where contact runoff would accumulate in the low area of the cell that we could pump right into the leachate valve houses. And we sized the storage area for a 25-year, 24-hour storm. So we built a lot of contact water capacity within the cells.
Great. Is your design report a publicly accessible document?
You know, I went online and looked in anticipation of this question and did not find it posted. I imagine it's available through DOE if one spends time digging, or perhaps through a FOIA request. I spent a few minutes looking and I could not find it online.
Yeah. What types of calculations/assumptions went into the determination of the 3-foot thick compacted soil/clay liner?
This was another ARAR requirement, both from federal regulations 40 CFR 264 and the Ohio Administrative Code. For hazardous waste landfills, they both require that the secondary compacted clay component of the liner system be 3 feet thick. We also know that 3 feet is sort of a commonly used thickness. 2 feet and 3 feet are the most commonly used thicknesses for compacted clay liner. And even if we hadn't had the ARARs, we would have, for this application, tended towards the thicker liner.
Great. Regarding the waste soil/selected waste immediately placed on the operations layer, did you have to stabilize or fix the soil to immobilize the contaminants before it was placed?
No, we didn't immobilize or solidify any of those materials. The fate and transport modeling that had been done for the feasibility study for this project showed that the mobility of the constituents of concern were not very high, and that transport times and transport amounts would be small without any fixation.
Right. You sort of went through this in your webinar, but someone asked, what are the components of the cover system? If you could just run through them again.
Yeah, I would refer everyone to slide 18 of the original presentation that shows a 9.75-foot cover system that starts with a contouring layer, then a compacted clay cap, a geosynthetic clay liner, a geomembrane cap, geotextile cushion layer, a 12-inch thick cover drainage layer, a 3-foot thick biointrusion barrier layer, a granular filter layer, and then 27 inches of vegetative soil and topsoil on the top of this layer cake.
Rudy, what would you do differently if you constructed the site today?
Well, you know, that's not a theoretical question, Jen, because we're actually involved we were involved in the design and we're now involved in the construction of another DOE site, Portsmouth, the Portsmouth Gaseous Diffusion Plant, which also happens to be in Ohio. And we essentially have the same liner system, the same gravity, drainage, leachate collection approach, many of the same things from a design philosophy standpoint that we had at Fernald. And so most of the differences relate to details. For example, we reconfigured the valve houses, which is the place where all the leachate flows to go into the force mains that take it to the wastewater treatment plant, to be more user-friendly, to have different valves, to reduce scaling, to have better ventilation for safety, and things of that nature. So there were a variety of mechanical things like that. We selected some different seed mixes for the final cover system based on lessons learned at Fernald, and so that's another change. We made some modifications to the stormwater management system as well, and so that's another area of some change. So there were some changes around the edges of the design, if you will, but for the most part, there's a lot of similarity. I'll also add that we obviously went back and updated all the specifications, updated CQA procedures based on advancements in our profession from the 1995-1996 timeframe to the 2010 2015 to present timeframe.
Great, Rudy. Well, if you make it to Portsmouth, Ohio, make sure you drive the Portsmouth bypass. Incredible bypass of Portsmouth through the mountains.
Oh, I'll do that, Tim.
Great. Can you share design information on your trial test pads, the size and testing criteria that you use for the test pads?
Yeah, I'd be happy to. Each test pad had 3 lanes. They were 50 feet long, not including the ramps. So the flat part were 50 feet long and 14 feet wide, which is 2 full passes, 2 full width of a Caterpillar 815B pad foot compactor. And we processed the materials by removing oversized rock. I think we had a 2-inch criterion for rock removal. We then used a transverse rotary mixer, a Ham Rayco 250, to actually blend and moisture condition the material. So it got more conditioning than most clay liners. We moisture conditioned to about 2% wet of the optimum moisture content. And in the 3 lanes, we compacted the materials to 95, 97, and 99% of standard Proctor relative compaction. And we had some error bounds on those things. And that equated to 4, 7, and 10 full width passes of the A15B. We measured, as you can imagine, nuclear moisture and density. We did sand cone testing. We took Shelby tube samples, and we of course did the sealed double ring infiltrometer testing that I highlighted in my presentation.
Right. Okay. Did you have any primary or secondary settlement instrumentation in the landfill?
We started to have that instrumentation, and we were hoping to have that instrumentation, but due to a budget cut at DOE right around the time it would have gone in, it was nixed. So no, we don't.
Okay. What geochemical mechanisms could be attributed to the substantial reduction of uranium concentration in the LDS compared to the leachate collection system?
We don't think the difference is due to leachate leakage through the primary system and then the attenuation of constituents by absorption onto the clay liner material. We actually think that the water in the leak detection system is from another source, possibly in part from construction. But we've actually never completely put our fingers on it. But the concentrations match up well with the native soils below the liner system. So as I talked about in the presentation, we don't think it's leakage through the primary liner. I will say, however, though, that the retardation coefficients, the soil water partitioning coefficients for these constituents are fairly high in the environment of the landfill. And so to the extent that there is any movement occurring, we would expect to be seeing a retardation of the radionuclides in the primary liner material.
Good. Last question from the live webinar question box. What is the composition of the 12-inch contouring layer at the bottom of the cover system?
It's essentially the same till material as the compacted clay liner material, and it was placed the same way. Really, the only difference was that we didn't require quality control and quality assurance testing in the way we required for the compacted clay liner.
Okay, so Rudy, now I'd like to turn to the post-webinar questions that we received through the post-webinar survey form. We received over almost 30 there as well. So here we go. Was the 80 mil HDPE geomembrane also used for the geomembrane cap?
Yes, yes, it was.
Okay. Is or was air quality monitoring being performed around the facility? And I guess this means during construction and demolition.
Yes, there was extensive air quality monitoring, both for particulates and for radionuclides.
Yep. Is there any subsidence of the cover anticipated due to the composition of wood or other organic materials in the waste?
I wouldn't say, Tim, that we anticipate it because we tried to pack around it. And, you know, the type of material being considered in this question, we called category 2 waste. And we placed it in bundles, not more than about 24 inches thick, and placed compacted soil all around and over it. So we're not expecting subsidence, but we nonetheless conducted analyses of what would happen if one of these bundles closest to the cover system had underwent some significant subsidence, either due to raveling or decomposition. And we came up with the type of analysis that we used of a settlement at the middle of a depression of on the order of 0.4 to 0.6 inches. So not a whole lot. And the tensile strains at the clay liner level or clay cap level associated with that was less than 1%. So even for the design scenario we considered, we didn't see a problem.
Rudy, were there any challenges with design changes occurring during the construction phase?
The two things that stand out, Jen, to me were one, the amount of dust suppression water that was used. Almost every day, if it wasn't raining outside, dust suppression water was used at the working face, and that was more than we had anticipated in design or accounted for in design, as I described in my presentation. The other was not within the landfill, but in the leachate transmission system from the valve houses to the wastewater treatment plant. We had started out specifying electrofusion couplers to connect the HDPE pipe sections. And we had some real challenges with the contractor in meeting the QC/QA requirements for those. And we had to go back several times and conduct a forensic study and figure out what was going on and make some corrections. I'm not saying that as an indictment to electrofusion couplers, but it was, and I'm trying to remember exactly what the problems were, but on this particular job, we had some challenges and it took a while to sort them all out.
Great, Rudy. Next question is, was there a difference in the actual waste volume generated from the demolition and your design volume? And if so, how was the difference addressed during construction?
There was a small difference at the end, and the way we handled it, we recognized that could happen, and DOE recognized that was a possibility. So we made the last cell flexible in the sense that we could extend it or shrink it under our permit by a certain amount based on the anticipated amount of waste as we were getting towards the completion of the job. And that's what we did. We just moved the boundaries a bit.
Great. How did you show that the liner penetrations would perform as designed for the intended lifespan of the facility?
We didn't actually demonstrate that. What we demonstrated was that we used the best possible materials in each case, the HDPE flat stock and the HDPE geomembrane, that we caused them to be constructed in the most secure way possible. That is, welding the geomembrane to the flat stock and not to a round pipe, and a whole variety of things like that. And the geometry, when you see this, the geometry of this whole contraption that we designed. And by the QC testing, I talked earlier about building this double wall system where we could actually air pressure test in the middle, which we did, and then filling it with bentonite. So all of these things taken together gave us the most assurance that we could reasonably get that the system would work as intended.
Great. What is the minimum SCR, stress crack, requirements for the HDPE geomembranes?
Yeah, if you remember, I mentioned that was ASTM D5397. And back in 1995, when we were designing this, the standard specification was about 100 hours to failure at, I think it was 600 PSI. Does that sound right?
Yeah.
Tensile load. And we tested 5 different commercial geomembranes and had 3 of them pass a 500-hour requirement, and we based the specification for this facility on that requirement.
Great. Actually, the next question's sort of similar to that. For the stress crack requirement for the HDPE pipe instead of the geomembrane used in the leachate collection and the leak detection systems.
Yeah, well, we tested using a different method, D1693, standard test method for environmental stress cracking of ethylene plastics. And this is the more common procedure for thick wall pipe. And the requirement was that, and it's a completely different type of test, although you still insert the samples in the IGPL solution. This is a different type of test, and you count the percentage of samples that fell. And so the criterion for the pipe was that not more than 20% of the samples could fail within 192 hours within the immersion bath.
Okay. Rudy, I just noticed I missed one question. What were the expected / measured radiation levels in the landfill cells?
Well, I can only partially answer that. Because we didn't do the dose modeling for the workers. You know, radionuclides have an activity. That's how many disintegrations they have. I mean, are they an alpha? Is it an alpha particle, a beta particle, gamma, some combination? And what's the energy of the particles? And we had waste acceptance criteria for what could be allowed in. So, for example, for uranium 238, the maximum allowable activity of any sample was 346 picocuries per gram. And for technetium 99, as another example, it was 29.1 picocuries per gram. Now, there were health physicists that took that data and converted it into total dosages and effective dosages. We weren't part of that, but part of what established these waste acceptance criteria were acceptable exposures for workers at the site.
Great. Now, going back down the list of questions, how was the HDPE wrinkle management performed during construction?
Well, remember, this is back in 1995, so we didn't have quite as stringent guidelines as we have today, but I think we had some good ones. We worked hard to try to minimize wrinkles, and we had a number of requirements. For example, one of the requirements was that at the hottest part of the day, the peak wrinkle size couldn't be more than 4 inches. And and there was a QC requirement for that, and then that was something that was part of the construction quality assurance monitoring. We also required, for example, that placement of granular material on top of the geotextile cushion that went on top of the geomembrane not occur during the hottest part of the day, and in fact occur in the morning, not at the crack of dawn, because you don't want to do it immediately, because if it's a cold night, the geomembrane can be under some tension. But in like the mid-morning time frame, before the geomembrane will get hot from atmospheric heat, and so we used that combination of placement strategy for the geomembrane, and then placement strategy for the overlying leachate collection system to try to minimize wrinkles to the extent we could.
Right. So Rudy, just to make the questions even longer, so did you use black or a white geomembrane, just out of curiosity?
Everything was black, and Tim,
Oh.
I don't recall as a fact, but I think that's all that was available in '95. But I could be wrong about that. It just seemed like such a long time ago.
Okay. Okay, next question, Rudy. Did the construction use the same type of geomembrane resonance stabilizer package in the primary composite liner system as well as the secondary?
Yes, it did. Yes, it did.
Okay. I was curious about the half-life of the radioactive material. After 200 to 1,000 years, will the landfill be significantly less radioactive?
The answer is yes and no. The design, the half-life for something like strontium-90 is only 65 days, and I think tritium is 22 years, or something like that. But for uranium-238, the half-life is 4.5 billion years. So, and for technetium-99, which was a chemical of concern, I want to say it's on the order of 200,000 years. So for some of the radionuclides, the design life is very long compared to, I'm sorry, the half-life is very long compared to the OSDF design life.
Great.
The next question up is, what are the maintenance and design considerations for long-term stability and protection of cover systems for erosion or from erosion?
Yeah, great question. So the cover system is inspected on a quarterly basis, and maintenance will include the filling in of gullies and rills. Remember, I mentioned that we designed using the available methods to prevent gully initiation. I think it's been partially successful, although we still see some gullies occurring. It's filling in any rodent holes that are found, and typically these are quite small, but they are filled in when they're found. It involves cutting down woody vegetation, and in more recent years, they've begun a process of controlled burning of the cover system grasses to allow them to rejuvenate themselves, and it's part of the ecological plan for the OSDF. So those are the things being done.
Great, Rudy. We're on the home stretch. So one of the photos of the OSDF that you showed in your presentation shows it's near the Miami River. How was the potential flooding from the river and lateral migration of the river considered in siting and design, i.e. long-term behavior, 100, 200,000, 250, 1,000 years shows river flooding in the area?
Yeah, that's another great question. Let me start with the latter part of that. While they look quite close, the river itself is about 0.8 miles away from the closest point to the OSDF, and that's to the outer berm of the OSDF, not the waste mass itself. So we coupled that with geomorphological studies and related to the extent that there were historical aerial photographs, and other lines of evidence to conclude that the rate of migration of the meander bends in this area are quite slow. The glacial tills are very dense. They're quite robust. The river really is not moving very much. So in terms of the river encroaching on the OSDF, we really don't have a concern about that. With respect to flooding of the river is well below the plane of the OSDF to begin with, but notwithstanding that, we have designed the containment around the entire facility for the maximum credible flood, with freeboard on top of that. So it's quite a conservative design.
Great. Rudy, what is the location of the horizontal well in plan and cross section?
So the horizontal well is a perforated horizontal pipe that immediately underlies each sump, each leachate collection and leakage detection sump of the on-site disposal facility. And it's been designed to collect water that accumulates in the backfill for the well, and then that liquid drains by gravity to a collection point where it's monitored for both quantity and chemical quality. And what we saw in the presentation is that there's very little water being collected, small amounts, and that the uranium concentrations are close to but lower than their uranium concentrations that we're seeing in the leakage detection system. And in fact, those uranium concentrations are believed to be associated with the glacial tills from infiltration of impacted waters at the site from the timeframes of plant operation and the modeling, the fate and transport modeling and human health risk assessments that have been conducted have shown that they're not of environmental concern. I should mention, I don't think I mentioned this in the call, that there is nonetheless, having said all that, a very large pump and treat system that is pumping water from the Great Miami Aquifer and treating it in a water treatment plant to remove uranium before re-injecting it. But this is not from uranium infiltration in this area, but from uranium infiltration to the aquifer and other parts of the site.
Great, Rudy. That actually dovetails nicely with the next question, and it is there a wastewater treatment facility at the site? And if so, how many years is it intended to operate? And what are the conditions when such facilities operation is no longer deemed necessary?
There is, and it's primarily intended to treat groundwater that's pumped out. And I don't recall here how long that is intended to continue to run, but it's for a number of additional years. And our contribution from the OSDF, now that it's closed, is a minuscule amount of the total flow. We've designed the OSDF to enable DOE to make a decision at a future date that they can actually just open up the leachate collection system drains and let them spill into the environment, that there's so little flow coming out at such low radionuclide concentrations that there's no environmental impact to just allow them to gravity drain into the environment. When that time will be, we did not try to determine in our design, but we've created a passive end state that in 30 years or 50 years, that decision can be made based on the performance of the facility.
Great. Okay, Rudy, we've got 5 questions left and about 9 minutes, so hopefully we can meet that. Would you explain the reason of the measured leachate collection flow rates being higher than the HELP model predictions?
Yeah, if you recall during the presentation, I identified 2 reasons. One is that the cells, notwithstanding our sizing of the cells, as I described earlier, many of the cells were open longer than we had anticipated during the design. We thought they'd be zipped up more quickly with the final cover system. And 2, the use of almost every day this dust suppression water. That was something we had not accounted for in the design when we did the HELP modeling.
Right. Okay, next is, I'd like to know how to separate the cells during phases of operation. When cell 1 is filling with radioactive waste and contact water may wash down to cell 2, what is needed to do a proper separation of the cells, adjacent cells?
Yeah, good question. Well, when we build the liner system for cells, we put an intercell berm between the 2. So if you remember, the downslope direction is west to east. We have an intercell berm between cell 1 and 2 running the whole way, and it's 5 feet high. And the liner system for cell 1 goes up over the berm and then connects at the top of the berm, the liner system for cell 2. So there's no route at the liner system level to go to cell 1 to cell 2. Then when we fill cell 1, we don't fill it right up to the edge of that intercell berm. We leave a drainage ditch at the edge of the cell within cell 1. So any contact water that runs off in the cell down to the low point, to the leachate catchment area I described earlier. And it's only when we start operation of cell 2 do we allow the waste in cell 1 to go over the intercell berm into cell 2.
Right, makes sense. Okay. Rudy, at the end, you lost your internet connection and didn't get a chance to talk about your last two slides, which discuss the Fernald Preserve and the current uses of the site.
Yeah, and I'm sorry about that snafu, but I think it's really fantastic that this former, DOE plant that was part of the nuclear weapons complex in the United States during the Cold War is now a 1,000-acre nature preserve that is open to the general public. Birders go there, hikers go there, people go there to enjoy nature. I know I'm on their mailing list. Anyone can be on their mailing list, and about once a month I get a report on what's going on and programs they have in the clubhouse there. And one came just in the last week or two. A beautiful owl perched on one of the trees out there, and it just makes you feel really, really good about having been able to contribute to a project like that.
That's great. Okay, great. Last two questions. Why place the lowest point in south area where the thinnest gray glacial till is located? At the north end of the facility, the gray glacial till is much thicker, and that could have been a good place for the lowest spot.
The answer to that is, in some ways, yes. However, if you tried to lay out the low point in the cell to be the lowest cell to be on the north side, you would have accomplished that first goal, but it would have been very hard to make the grading work for the remainder of the facility. And we looked at that pretty carefully when we designed the cell. It would have taken much more excavation and much more filling to lay out the 8 cells for the OSDF, and it would have been more difficult to make the gravity drainage work. And we felt like the gray till and brown till are such high quality materials, coupled with all of the other environmental controls, we had an adequate thickness of material to achieve our design objectives.
Right. Okay, Rudy, last question, promise. What is the level of seismicity that the OSDF facility is designed for?
I meant to go back and look this up before this podcast. And Tim, sitting here, I don't recall the number. It was, I believe, either the 2% in 50-year, or perhaps the maximum credible earthquake that we designed for. And I believe that the ground motion, and I'm going completely from memory, was likely on the order of 0.15, maybe a little bit more than that. And I'll also mention that we designed the facility for zero displacements under a pseudostatic seismic analysis. So we didn't allow, for example, 3 inches of displacement on the liner system. We just went for a zero displacement, which isn't super brave because it was an easy criterion to meet at that shaking level.
Right. Okay, Rudy, thanks so much. Geez, we went through 30 plus questions. Thanks so much for joining us again. And that's all the time we have today. If you have additional questions or would like additional information, please contact Rudy Bonaparte at rbonaparte@geosyntec.com, or you can email me and I will forward your question or request on to Rudy at fabricatedgeomembrane@gmail.com, or visit the FGI website at fabricatedgeomembrane.com. Hey, Rudy, thanks so much for a great webinar and answering all these questions.
Thank you, Tim, and thank you, Jen, and take care, everybody.
Great. Thanks,
Thanks, Rudy.
See ya.
Bye-bye.
Bye-bye. Okay, great. Thanks again, Rudy. We really appreciate it.
Oh, you're still on.
Well, yeah, I'm just logging off right now.
Great, and I am too.
It took a lot of your time, but we really appreciate it. And the people who take the time to type in the questions, they will be so excited to get your answers. So we appreciate it.
Great, great. All righty, take care.
Take care. Thank you. Bye-bye.
Bye-bye.